Hi everybody! Today I want to talk about kinematics of particles. Please write yourself a huge title, Kinematics of Particles. Because both kinematics and particle is an important term in terms of dynamics. Okay, let's start with kinematics. Kinematics is the branch that develops the relationship between position, velocity, and acceleration. So, I guess you all remember these terms from physics class, but I want to make sure that we understand the same thing from these terms. So, first, what is kinematics? Kinematics is actually the relationship between position, velocity, and acceleration. Let's recall what are these terms from your background. Position. When I say position, I indicate a distance between a reference point and the point of the object at that instant. When I say velocity, I indicate the rate of change in the position, and when I say acceleration, I indicate the rate of change in velocity. But let's develop a base so that we speak the same language in terms of these terms. Let's start with position. So when I say position, what I understand is actually if I have a particle moving on a straight line, let's say, if the particle starts its motion at this point, then this point indicates its position. But in order to make it a scalar or vectorial quantity, I need to define a reference point. So let's put our reference something like this. If we have a reference point like this, then the distance between this position and the reference is called position. And we usually use letter S for position. And if the particle moves from this position to another position after a while, let's say this position, then the particle is displaced. And if this is initial point, and let's say if this is final point, then we can put letter I as a subscript, and we can say that Si is the initial position, and we can do the same thing for final position. We can define an S final with respect to reference, and then we can say delta S is S final minus S initial. I put a vector sign here because, as you can see, the positions are given in terms of two quantities. One, the magnitude, which is the distance between the reference point and the particle's current position, but also it has a direction. I can say that it is towards right. Okay, and also the difference between these two positions, which is given as displacement, which is another important term. Displacement is also a vectorial quantity because I can say that the particle moved from left to right. Okay, so in addition to the position, also we need to understand the notion of displacement. And two important things. First of all, these two quantities, position and displacement, are vectors because it is indicated by both magnitude and direction. And the second important thing here, position and displacement are different. Position indicates the current state of the particle, but the displacement indicates the difference between two positions within a certain amount of time. Let's say if we start from t equals ti, and if we spend some time t equals t final, then the total time spent between these 2 points is t final minus ti. Okay, so these are the basics about position and displacement. Let's talk about velocity. So as we already indicated, velocity is the rate of change in position, and in this sense I can write v as delta s over delta t based on this definition. Okay, but this definition of velocity is in average sense. Okay, so this is in average sense. So if I consider the particle from initial position to final position, of course it will pass through lots of points and it will end up here finally. But between these 2 points, it will move from different points. Now, if I want to focus on at an instant, okay, let's say if I want to focus on this instant, what is the velocity at this instant? What I need to do, I need to move in terms of time. I need to focus on that specific time. So therefore, I need to also define an velocity in instantaneous norm, which means if I limit by time goes to 0, delta t goes to 0, then I can focus on that specific time. So from math classes, you may remember this limit gives me differential term, so ds over dt. So in instantaneous form, the velocity is given by differential of position with respect to time. So this is one kinematics relation that I want to use. By the way, because delta s is a vector, I want to put a vector sign here. So in terms of instantaneous manner, velocity is given by ds over dt. And let's indicate that this is instantaneous velocity. And the relationship between position and velocity, this relationship is a kinematics relation. So let's talk about acceleration then. As we already indicated, acceleration is the rate of change in velocity, right? And in this sense, I can write A as delta V over delta T, but again, this is in average manner. But similar to the instantaneous velocity, I can focus on a specific instant and then I can define an instantaneous acceleration, which is when limit delta t goes to 0, delta v over delta t, and this will turns out to be a differential of velocity with respect to time. So this is the acceleration, the definition of acceleration in terms of velocity, and it is actually differential of velocity with respect to time, and this is an instantaneous acceleration definition. So this is the second kinematics relation, which is very important, which we need to use for future calculations. Now here we have the relationship between position and velocity, and we have the relationship between velocity and acceleration, but sometimes we may need to develop a relationship between position and acceleration. So what do we do in this sense? Then if we can eliminate the time from this equation, these equations, then we can develop an acceleration position relation. So my question is this: what about relationship between position and acceleration? In order to develop this relation, I can eliminate the time from the two relations I already write. So V is equal to ds over dt and A equals dv over dt. From here I can write dt as ds over v, as you can see here. And if I plug in this back to here, then A is going to be dv over ds over v. And then if I write this ADS equals VDV. So this is another kinematics relationship, which is the relationship between acceleration, displacement or position, and velocity. What we did here, the time is eliminated. Time is eliminated in relation. So we have these three very useful relationships. So as a result, or as a summary, we can say V equals ds over dt. A equals dv over dt. If we don't want to deal with time, as an alternative term, we can write ADS equals V dv. So these are the three important kinematics relation we usually use in our calculations. Okay, now you all understand what is kinematics. Kinematics is actually the relationship between position, velocity, and acceleration. In other words, what happens in a particle as the time goes, what are the changes in position, what are the changes in velocity, and what are the changes in accelerations as the particle moves or displays. So now I want to talk about particle. Okay, so particle is another important term because on the title what we said, kinematics of particles. So we want to define the particle. I guess you all know the meaning of particle. Particle is actually a small dot or infinitely small dot which we can represent an object. Okay, so when we say particle, we usually put a dot, and this dot represents the part itself. But we know that when we say particle, it doesn't have dimension. So when we say particle, we mean actually two things: no dimension. So it is just a point. Okay, so it is like we don't talk about length, we don't talk about the volume or anything. Everything is represented on a single dot. So it means there is no dimension, and also the mass, I mean in a better representation, inertia is represented at a single point. represented on a single point. So, of course, this is an idealization, which means there is no such thing as a dot, okay? Even though very, very small particles have dimensions. This is an idealization, but it's a very good idealization that we can think of all the forces are located at a single point, let's say. So, a particle is an idealization, but it's a good idealization. But when? So, when do we idealize objects as particles? So we may have two answers for this question, okay? Once the actual size of object is very small, okay? In case actual size of object is very small, or if the size of the object is negligible compared to the space that it travels, okay? Or another case, the size of object is small compared to the space object travels. So what do we mean by that? Think about a car which travels from Bursa to Ankara. So think about a car, let's draw a car which starts at Bursa and it travels to Ankara. Okay, it travels to Ankara, and the distance between these two locations is about, let's say, 400 kilometers, okay? But what is the size of the car? It's approximately 2.5 meters or 3 meters, okay? So compared to the size of the car, the distance traveled is huge, okay? So we can say this is about 3 meters. Of course, it varies depending on the car. It's just an approximate. But the distance between these two locations is basically 4,000 meters, let's say. So compared to the distance traveled, the size of the car is negligible. So once we model this motion, we may consider car as a particle. So we can just represent the car as a particle. So this is one example. Why do we consider an object as a particle? Another example, of course, if this is the Earth, and if we have a satellite, let's say if this is Earth, if we have a satellite which is very, very small, satellite, if it is very, very small compared to the size of the Earth, and actually when you compare to the size of the space, it is very small. So we can model the satellite as a particle. Of course, in detailed engineering calculations, we don't do that. We need to consider the size and inertial effects of rotation and stuff of satellite. But once we model the general perspective, like once we look from outside, let's say we look from Mars or we look from Moon, then we can consider satellite as a particle, okay? So compared to the size of the Earth, the satellite can be considered as particle. So I guess you understand now what do we mean when we say particle. So, and for example, an atom can be considered as particle compared to the size of the Earth we live on, the atom is a very small thing. So if we want to model the motion of the atom or motion of the electron around the nucleus, let's say, we can consider electron as a particle because the actual dimension is actually small. So as a result, particle is an idealization. So let's write it down as a summary. Particle is an idealization. Particle assumption is an ideal definition so that we can ignore the size of the object. And what is the benefit of doing this? The benefit is this: we don't need to deal with inertial effect of the object itself, rotational inertial effect of the object. So the benefits here, we can ignore rotational inertia of the object, because as an object which doesn't have a size cannot do rotation. Once you think, so in order to talk about rotation about its own axis, you need to think about a size. So if the object doesn't have size, you cannot talk about axial rotational inertia effects of the object. So